moving forward to execute that technology, create an own blockchain, and prototyping on the team. So, okay, I would like to invite the first speaker, Andrew. He will make a small introduction about himself and about his first presentation, Randomness in Proof of Stake.
Hello guys, thank you for coming. It's for you, Andrei, it's for you. My presentation about randomness, but not only in proof of stake. I will talk about randomness in blockchain in whole field. So my name is Andrei Soborin. I'm developer in Pandora. I'm a researcher. I think about protocol consensus, about randomness. Oh, I think I need to go here, yeah?
Or down.
Okay, I will try. So, I think about consensus algorithm, about randomness, and sometimes random look like this code. It's very good code. Sometimes we write code like this. Okay. But I think it's not a good solution in production. What we need in production? We need in production something like this. And we try to create distributed AI, and for distributed AI we need censorship-resistant ledger. And for censorship-resistant ledger we need censorship-resistant consensus algorithm. And for censorship-resistant consensus algorithm we need honest random. So does it matter? Yes, it's matter because in P2P network we need mechanism to lead a election, because in distributed network we have no one authority which can update ledger. So if we want that many participants, if we need to write many participants to update ledger, we need a solution to create order of this update or other stuff. So structure of my speech. First of all, I will talk about proof of work. Then I will talk about preset random in blockchain system. I will talk about naive random, commit reveal scheme, and I will talk about verifiable delay function, Shamir secret sharing, and scaling of Shamir secret solution. So when we talk about random, it's first random picture. Okay. First of all, proof of work. Proof of work and the Satoshi Nakamoto consensus. It's first distributed network which have immutable ledger, which have censorship-resistant ledger. So, how Satoshi Nakamoto consensus achieves this stuff? First of all, we can think about proof of work as decentralized lottery. That means that anybody who can participate to protocol, they can try to generate block. If its block will valid, they can update ledger. We have in proof of work, we have probabilistic First of all, in proof of work, we can think about proof of work as one hash, it's one ticket. So that means if you try to calculate one block, you will calculate one hash. So it's like you buy one ticket in distributed lottery. It's permissionless free lottery because anybody can create hardware to mining, anybody can buy hardware to mining, and anybody can participate to network and use it. If we talk about proof of stake or another variant of consensus architecture, for example, proof of stake, proof of authority, proof of reputation, we need another random generator in the blockchain. So, first of all, I will talk about preset random. That means that we can get random from for example, from radiation or from markets trading. We can get seed of market data, and we can present it only one time in consensus algorithm, and we will use this seed of random in we will use it all time. So what we achieve?
Is it possible to do something with the volume? I mean, it's kind of...
Yes.
Okay. Oh, I think it's...
There.
Yeah.
Super
Cool.
loud.
Okay.
Super loud.
So what we achieve? What we achieve? For example, we can preset seed of randomness entropy, and we get something like this. We have 4 nodes, and each node have a number. For example, user A, node A have number 1, user B have number 2, user C have number 3, and user D have number 4. That means that in first block will sign by user A. Second block will sign by user A. Third block will sign by user B. And we can see that if you are user C, you didn't like this random, and you will try to cheat. And if we have dynamic system, any node can change number. For example, if we sort our list by address or by size of money, user C can change number, and they achieve another permission to sign the block. So it's not a secure solution. Naive random. I will talk about naive random. That means that each participant of protocol just provide part of random. That means that user A provide 4, 3 to 5, user B provide another number, user C provide another number. And if user D is malicious node, user D can wait before user A, B, and C provide number, and user D can combine random. So if they provide, for example, this number, you get one result. If user D provides another number, they get another result. So only one node can cheat and can fully control of random in this algorithm. So it's second random picture. Committer wheel scheme. Commit reveal scheme is modification of naive scheme of random generation. That means that we have two stages. Commit stage when user provide hash of random, and reveal stage where user provide random. So user A provide hash, user B provide hash, user C provide hash, user D malicious node. So user D can provide a hash of random number, but if user D want to cheat, they can, in reveal stage, they can select I provide my number or I just provide nothing. So user D can select between two variants of randoms. That means that if we have one malicious node can select between two variants of random. If we have, for example, hello 1000 node, and if 50% minus 1 is malicious node, we get this very big size of random. So if 50% minus 1 node conspire, they can select anybody. Another approach of random is verifiable delay function. What does this mean? It's approach about this approach. Vitalik Buterin talk and Vlad Zanfer talk about verifiable delay function, and it's function which have strong mathematic deterministic time of calculation. How we achieve deterministic time of calculation? That means that this function, we cannot scale computation of this function to many computer. And if we will calculate it in one computer, we get very limited time of calculation. So we can say, okay guys, for this function we need 10 minutes of calculation. Anybody who tried to calculate, anybody need to spend 10 minutes. So if we have very small time to provide randomness, nobody can pre-calculate this function, and nobody can know which randoms they get. So if we have only one honest node in random algorithm, we get strong random. But that's about how we can verify this function, or how we can calculate this function, and this slide about how we can verify. By the way, in this function we can verify computation in a fast way, but if nobody know result, we need very long time to calculate it. So each participant who will see history of blockchain, they can get fast approach of validation. The problem of this approach it's ASIC resistance. We can provide strong scientific proofs that we can calculate it only in one processor, but Jihan Wu can create ASIC. It's because Jihan Wu is magician. They can do ASIC for any hash function, any strong cryptographic tools. So we need strong proofs, and this approach is very experimental in this time. Insert random picture, and I will talk about Shamir secret sharing. Shamir secret sharing, it's a cryptographic primitive which we can use to, we have data, array of bytes. We can split it to, for example, 5 pieces, and 3 pieces of 5 can restore this data. We can use it like 3 of 5 or 5 of 10. You can configure it as you want. So I propose algorithm how we achieve honest random using Shamir secret sharing. We have a public key provider, we have 3 stages, and we have in first stage public key provider, which provides a public key and we can use it to encrypt data. In second stage, random data provider splits random to Shamir secrets part. Then random provider encrypted using public key encryption algorithm. And in stage 3, each provider provides private keys. It means that anybody who encrypts part of random using public key reveal it, and nobody knows final result before all network gets final result, and we get a cool algorithm for random generation. But in this algorithm we have one problem, it's scaling. So first of all, we have a long time to calculate Shamir secret sharing algorithm in big digits. That means that if we want to, for example, calculate it for half of 1,000 part of secret, we need 1 second. And if we want to calculate it, for example, for 2735 participant, we need more than 1 minute. So if we try to scale it, we get very big time of calculation. So what we propose in another problem is size of data. That means that if we have 1,000 random provider, and if they split random to 501 pieces and encrypted, we get very big data. We get 6-9 megabytes, and